This video is going to cover section 2.2 in conditional statements. So what is a conditional statement? Well, for a statement that has two properties P and Q, the conditional statement is from the form if P, then Q. In notation, we have this P and we have an arrow going towards Q, and it's read P implies Q. In terminology, P is the hypothesis or the antecedent, and Q is the conclusion or consequent, or sometimes even the thesis. One example of this would be if n is an even number, then n equals 2k for some k that belongs to the integers. Now, all of this mean the same thing as if P then Q. We're going to have some alternate phrasing here. We can say that P implies Q, P only if Q. We can also say Q if P, Q whenever P is sufficient for Q, or Q is necessary for P. These are all equivalents and mean the same. Now, the truth table for P implies Q is always going to be true in general unless we're starting from a true hypothesis and we're getting to a Q consequent that is false. So if true implies false, that's the only case where the implication is going to be false. When P is false, we call P imply Q backwardsly true, since it can't be disproven. So we're starting from something that is false, and so it can get to anything, but the implication is correct. Now, why is P implies Q true when P is false? Well, let's make an example here. Your professor says if you earn an A on the final, then you get an A on the course. So let's say the student gets A on the final. So gets an A on the course, and the professor kept the promise. This is true. The implication is true. The antecedent is true. The consequence is true. Now, if the student gets an A on the final, but he gets a B in the course, then the professor broke the promise. So the implication is not correct because we got the antecedent, but we did not got the consequent. So in that case, the implication is false. Now let's say that the student gets a B on the final and he gets an A on the course. So in this case, the professor kept the promise anyway. And if the student gets a B in the final and he gets a B in the course, the professor gets the promise. So the implication is not broken. The fact that the student gets a B in the final, but got an A in the course, maybe because average other things, is not breaking the implication. The conditional only makes the claim about what happens if the hypothesis is true. Okay? So otherwise, it's just going to be what we call backwardsly false. But notice that this example showcases that it's all about the final implication. Are we keeping the final implication or not? Now, the conditional can be seen as a disjunction. We have that P implies Q is equivalent to not P or Q. So this means that if we have P implies Q, it can happen two situations. We can have that P is not happening, not P, or Q. Any of those two things is going to happen. We can prove that by truth table, by showcasing that this is logically equivalent. And as you can see, they both P implies Q and not P or Q, they have the same true values. So we can use pretty much this to interchangeable if we're trying to make algebra with symbols. Now, if we're going to negate P implies Q, then what we're essentially saying is that we have P, but we have not Q. So normally, the implication is P implies Q. Negating that is saying, look, We got P, but we don't have Q. So that's why negating P implies Q becomes P and not Q. Now, in worse, this will be to negate if P then Q, then P is true and Q is false. One example of this would be if my car is in the repair shop, then I cannot go to class. So there's two propositions here. P is car is in the repair shop, and Q, I cannot go to class. So the original implication is P implies Q, but I can also write a negation, which is P and not Q. The negation here will be my car is in the repair shop and I can go to class. So this means that the implication is not true. It's not correct. I'm negating that. Now, there's another ways of seeing implication at work, and it's the contrapositive, converse, and inverse. The definition of the contrapositive is an equivalence of P implies Q. So the contrapositive P implies Q is not Q implies not P. They're both logically equivalent. So one example of how will that look is, let's consider this. If n is divisible by 6, then n is divisible by 2. So we have two statements here. Statement number 1, P, n is divisible by 6, then and Q will be n is divisible by 2. Now the contrapositive is if n is not divisible by 2, then n is not divisible by 6. Those two things are saying the same. Now we can prove this contrapositive by truth table, and once again we're gonna see that this provides the same truth values on both of these statements. Okay, so columns 3 and 6 here are going to be identical in truth values. So sometimes what happens is that in proofs, which is something that we're going to do in the future, is much more easier to prove the contrapositive than the original statement. Now, the converse and the inverse are a couple implications as well. The converse is Q implies P. Given that we have P implies Q, the converse is Q implies P. The inverse will be negation of P implies negation of Q. Now, the converse and inverse are not equivalent to the original, but the converse and the inverse are equivalent to each other. If you think about it, the converse, the inverse is just the contrapositive of the converse. Now, in summary, the original P implies Q is equivalent to the contrapositive, negation of Q implies negation of P. The converse, Q implies P, is equivalent to the inverse, negation of P implies negation of Q. The original is different from the converse, the original is different from the inverse. Now let's look at these forms with a particular proposition. If today is Tuesday, then yesterday was Monday. So we have P, today is Tuesday, Q, yesterday was Monday. Those are the two propositions. Now the original statement, P implies Q, is if today is Tuesday, then yesterday was Monday. The contrapositive negation of Q implies negation of P will be if yesterday was not Monday, then today is not Tuesday, which is equivalent to the original. Now for the converse, if Q implies P means if yesterday was Monday, then today is Tuesday. This is not equivalent to yesterday. Yesterday could be Monday on Wednesday. The inverse, negation of P implies negation of Q, is if today is not Tuesday, then yesterday was not Monday. This is not equivalent to the original statement, but once again equivalent to the converse. Now let's look at some, the last statement will be the biconditional statement. The biconditional is called that way because we're doing implication on both directions. So we have P if and only if Q happens. And so the meaning is that P implies Q, but at the same time, Q implies P. And so we can say that the biconditional is essentially having P implies Q and having Q implies P at the same time. So those two will be equivalent here. Now, the truth table for the biconditional is if the P and Q have the same value, then it's true, otherwise it's false. So notice that when P and Q are true, then P equivalent to Q is true. When P and Q are both false, then P equivalent to Q is true. Otherwise, they're going to be false. One example in words of biconditional use would be today is Wednesday if and only if yesterday was Tuesday. Notice that this works on both directions. You can say yesterday was Tuesday if and only if today is Wednesday. You can go backwards on it. Now let's talk about necessary and sufficient conditions. Let's say that R and S are statements. R is sufficient for S means that R implies S. Having R is enough to guarantee S. If R occurs, S must occur. Now, necessary condition, though, is on the inverse direction. We have R is necessary for S means that the negation of R implies the negation of S. If something is necessary, means that if it doesn't happen, then what we're expecting is not going to happen either. This is equivalent by contrapositive to the opposite, S implies R, which is essentially you cannot have S without having R. R is required for S. Now, necessary and sufficient will be R is necessary and sufficient for S will be the biequivalence. R is necessary and sufficient to X means R is equivalent to X or biconditional with X. Let's do some examples on this. First, for sufficient. Being divisible by 6 is sufficient for a number to be divisible by 2. So this means that if we have R divisible by 6 and X divisible by 2, this is an if-then form. And then if a number is divisible by 6, then it's divisible by 2. So it's an R imply X. Now in the terms of necessary, working regularly is necessary to pass the class. So we can have R to be work regularly as pass the class. The if-then form will be if you do not work regularly, then you will not pass the class. And this is also equivalent if you pass the class, then it's because you work regularly. And so the negation of minus R implies minus X will be equivalent to S implies R. Okay, so in summary, we have the conditional, which is the P implies Q, and it's false only when it's P is true and Q is false. We have the equivalence, P implies Q equals minus P or Q, and the negation of P implies Q is P and not Q. The contrapositive is P implies Q and is equivalent to negation of Q implies negation of P. The converse is just Q implies P and it's not equivalent to the original. The biconditional means P equivalent to Q means that I have P implies Q and that I have Q implies P. And necessary versus sufficient are conditions that are related to the conditional as well. R is sufficient for S if R implies S, and R is necessary for S if S implies R. Okay? Some common mistakes that happen here is that people confuse a statement with the converse. If P then Q does not necessarily mean that Q then P. So an implication in one direction does not necessarily mean the implication in the other direction. You gotta be careful with negating conditionals. Some people sometimes negate the implication by doing the implication of the negations. That is not how it works. The right negation of an implication is that the antecedent happened and we don't have the consequence. Now, the contraposited is always equivalent to the original statement, and this is going to be very useful in the future. And of course, confusing necessary and sufficient conditions. Sufficient is R implies S, necessary is S implies R. And we're going to need to practice this more so we can get the hang of how each of these statements and rules work. So we're going to see more of that in the example section for 2.2. But this is the end of the session.